Well, I was planning on saying some things that Nunu knows. So why don't we start? Yeah. All right, so what I thought I would do, Nunu asked me to lead a discussion, and I think part of a discussion is getting some of the background on the table. He sent me an email asking me to talk about this topic in light of what happened in Vienna. And so for those of you that weren't in Vienna, what happened was we had a meeting going on, and in the course of the meeting there became a great deal of interest in microtearing. And most of us that were interested in it didn't know what we were talking about, didn't know the history of the subject. So I wanted to take 5 or 10 minutes and tell you what has gone before, focusing on what's been relatively recently, and then open it up to what it is that we should be calculating and what we can, or whether we think this is interesting. And I think it is interesting. So I'll go back and talk about where the topic. This room is very strange when you're up here. It echoes. So I'll go back and talk about where the subject began in a minute. But first I want to not talk about what is the instability, but talk about under what conditions do we care. And I think the first situation where microtearing showed up as a possibly critical piece of physics was in this paper that Mike Kotchenreuther and I did in 2000, where it was originally something, well anyway, most of the paper is about what are STs going to be like, and these were before we had STs in the program. What will confinement be like? And the basic idea was that the strong E cross B shear, because of the large rho star in these machines and the strong neutral beam fueling that was expected for them, was going to give you pretty strong stabilization of the typical micro instabilities and leave you with things that were a little bit more exotic. In this paper, which was both an APS talk and an IAEA talk, we went a little further and we looked at a configuration. Sorry, this is one of those dreadful talks where people show slides from. It'll get better. We looked at an ST with a pressure profile like this, basically flat with some sort of pedestal assumed at the edge, and a self-consistent current profile, which is given by bootstrap current and a very small seed current on axis to prevent difficulties there. So the current and pressure profiles are both consistent with one another in terms of the inductive thing, and in the paper it says what the fraction is. I think it's like 90% non-inductive current. The transport from this thing is entirely neoclassical, so this is a self-consistent neoclassical configuration, and so all of the transport comes from neoclassical, and you might say that that's a dumb thing to do, except that all the micro instabilities are stable in this configuration. And that's what these pictures are. Or this is, 10 years ago. So the typical micro instabilities are growth rates down here compared to the shearing rate of the device that you would build. Let's see, this guy over here. Which one is it? Sorry, folks. Yeah, this guy. So this would be the low aspect ratio thing, and the typical instability rates were really much lower than the E cross B shear, and the rho star is pretty large because the B fields are pretty low in these machines. And the thinking was that it would be very exciting to look at those, but the problem is this point up here. This is a growth rate of a microtearing mode, and later when we fleshed out these things more, the basic idea became that if you were to make an ST with a high beta profiles that were starting to look like neoclassical, you would have strong microtearing in them. And so we were thinking microtearing is the dominant instability in STs. Well, recently, let's do this one. No, wait, hang on. This one here. This is a paper from Princeton, EPS paper 3 years ago by King-Lak Wong, who's doing fluctuation measurements. And in some configurations in STX and similarly on MAST, they find that they can get neoclassical ion transport. It's not particularly low because the field is low, so it's still substantial transport. But they've shut down the micro instabilities, and the only lost channel thermally is in the electron channel. And so there's a question going on right now: is that ETG turbulence, trapped electron modes, or microtearing? And in this paper from the Warsaw EPS, which isn't a terribly sophisticated look, but still they took a bunch of experimental profiles and used GS2 and some other tools to calculate the growth rates, and then they used a Rochester-Rosenbluth overlap type argument, which you can see in this paper if you want, and they used Jim Drake's saturation amplitude argument to figure out whether they would have whether they should be getting mode overlap from all these little islands that were being done. And this is the chi that comes out of all that when they use the full pressure gradient. And this is the chi that they should have been thinking about. This is we'll talk about that in a minute, what the instability really sees. And this is the experimental chi. And you think, gosh, 1 centimeter square per second, this is awesome, but much bigger than that. So this is the typical 25 meter square per second problem that exists on these STs.
How does that compare with the ion neoclassical that you mentioned?
Ion neoclassical on these STs is pretty low. If I remember, in round numbers, it's less than a meter square per second, chi. And they observe as much as 100 meters square per second transport in the electron channel. So the electrons are extremely anomalous in these machines. And so the issues are, we're just trying to sort out in the experimental community whether we should be worrying about ETG, trapped electron, or microtearing. So David Applegate was a student at Imperial that started when I was there, but finished with Colin and Jack. And he wrote a long paper on microtearing in MAST. And I wanted to take you through, I wanted to point out this paper because Nunu asked me to, what do we know that's relatively recent? So this is a 2007, just like that last K.L. Wong paper. And we're going to go through this in a little more detail. So he has a lot of work with Jack on what is the nature of the instability, what kind of islands do you get. But I'm going to do that more carefully in a minute. I wanted to show you, he did some work in here with Howard. Where is it, Howard? Oh, this is just MAST. Okay, so this is a nice long paper that got published, and then David left the field. So I have a copy of his thesis, and anybody that wants it, we could post it on the conference workshop to share. It's a long, careful treatment of all the physics of microtearing, and he turned off one term at a time, turned off various things, lots of opportunities there for benchmarking. As far as I know, there are things in there that didn't ever make it. There's certainly a lot of details that didn't make it into these papers. So Colin, for whatever reason, isn't here. And
can you tell us, okay,
so now I'm going to go into the instability.
Yeah, okay, so you're going to say about what drives it?
Yeah,
Okay.
yeah, I'm going to do all that. I just was trying to give a flavor of who's been thinking about this, under what context. And as far as I know, the only context in which microtearing has arisen as a serious issue is in the ST, and it's primarily because in the ST configurations, the combinations of beta, rho star, and so forth are such that the long wavelength instabilities are typically not there or can be made to be suppressed. And so now you're left with these smaller scale things, and that's what we're trying to figure out.
But the simulations we're talking about
Yeah.
were not done in the regime where those other instabilities are suppressed, were they?
Yes, they were actually.
So that's GS2 with shear.
Yeah. No. They were done, this was in the days where we just said if the shearing rate is 5 times the linear growth rate, then we're just going to ignore those. So yes, now that we know PVGS.
How do we ignore them in a code which would have to generate?
We'll get to that. Right, we can't. Except that actually you can stabilize in an ST, like Howard's STPP, the spherical torus power plant, you have enough stabilization from the geometry. Oh yeah, there's a Coulomb spherical torus power plant, which again is one of these devices. You know, it's got an eye in front of it. It's on the imaginary axis. So a lot of these devices have such strong geometric shaping and such high beta, a lot of Shafronov shift, that you kill all the long wavelength instabilities with drift reversal and things like that. So it is possible. And I think in a week or two, before we leave the workshop, if we start looking at more exotic configurations, we're going to be in a situation where we can stabilize a good fraction of the drift type instabilities, and we'll be left with these things. Okay, so what are they? So Colin sent this for us to be the basis of a discussion, so I'm going to go through it in like 5 minutes, unless you stop me, and then we're going to call that the discussion, okay? So the topics that are covered in here is what are microtearing, and a little bit of the discussion, so I'm going to do that. I'll tell you a little bit about enmast, and then for this, we will decide what you're interested in. So I think everybody here knows, but there's a couple of non-fusion people, so let me just say there's some parity issues for instabilities in tokamak geometry, and there are instabilities which move a particle radially as the particle follows a field line and has the E cross B drift working on it as it goes around the torus. And so those are instabilities which have so-called drift parity, and those are modes which phi, the electrostatic perturbation, is even about the outboard midplane on the outboard side. And then there's parity modes, the opposite parity modes, which the field lines themselves take a radial step as you go around the torus one time, and those are the tearing parity modes. So it's just even and odd eigenfunctions of a differential operator, but they have pretty different implications. And so tearing parity modes look like this. If this is the position along the field line, and this is phi, if I have no idea what he's really got here, but let's call this phi. This would be an even parity mode, and A would be A, which would give you the field perturbation, would be an odd mode. Conversely, if this were A and it's even, then phi would be odd. So either the field line takes a step as you go around the torus, because the net displacement, let's say that this is A, then the gradient of this is telling you the magnetic field in the radial direction. And as I go along here, I step out. I'm just integrating this curve. I go along, I take a step out, and then I stop stepping again as the slope comes back to 0, right? So I don't know if he has a picture of that. So the magnetic field takes a step if that's A. So when A is even, delta B's got the same sign along the equilibrium field line, and the field lines are torn. I like to think, Steve likes to talk about these as reconnectons, right? Have you heard him talk about that? So it's really quite simple. If you have a mode with odd parity in A, that's called a tearing, and if it's in the literature, those people are looking for instabilities. So here's some of the history. People have been using GS2 for some time. I've already told you these things. And more recently, the Gene group is getting into this and looking at microtearing instabilities. And one of the things we should do while we're here is get the codes a little better in agreement and understanding of what's what. And if you don't know, there's posters right outside the door here where various people have got results on this topic so that we can have that conversation. So what is the, let me get to what Steve asked, what Jim asked. Right. So there's two kinds of modes, and basically these are electron temperature gradient driven instabilities. So it's grad T E that drives it, and the signature of the mode from the literature is that the energy dependence of the collision operator is what makes the whole thing go. when we did a long series of calculations to see these odd parity modes that were showing up with a grad T, we found that it was sensitive to the nu E, grad T. Grad N is actually stabilizing. It was sensitive to things like beta and the geometric parameters, grad P and magnetic shear, and it didn't care at all what was going on in the ions. Typical current layer width in the nonlinear simulations was rho I scale. And in this Applegate series of papers, there's a lot of comparisons with Drake and Lee, Drake and Glad, and then with some work by Jack Connor.
Well, in these simulations, you said the current layer width is rho I. What's the mass ratio? This is resolving all the way down
Yeah.
to rho E?
Yeah, these are physical mass ratios.
There's some separation between the two?
It's physical mass ratio. Physical mass ratio, and this is what made David leave the field. I gave David the code and I said, GS2's fast, and you'll just find some instabilities and quickly write them up, and then we'll study the turbulence, and then you'll get your PhD. And he went away for a year and came back and said, this code is really slow. I don't understand what's going on. So he was looking at a mass discharge with a cube profile like this in some shape, and he picked off a surface and he started looking at the instabilities. And the typical kinds of eigenfunctions that he was getting are like this. And in the simulations that we all do, we go from -3 to 3. And to get resolution, he had to go from -240 to 240. And this was 10 years ago. So this was taking him, a month per run to do each linear thing. And so he got really frustrated.
This is fully gyrokinetic ions?
Yeah, fully gyrokinetic ions and electrons. So this is the phi perturbation. It's odd. And this is the vector potential perturbation. It's even and it's highly localized. So this is our tearing parity instability. They're going in the electron diamagnetic drift direction.
But this means there is a lot of small scale in the radio, the lower line, or not?
Well, it depends on whether you're talking about the field perturbation or the velocity perturbation. And so the field perturbation, okay, on this scale, this looks really narrow, and so you'd say it's a wide thing. But he's got a picture. Here's a typical island that he got. And this is in rho I. He's just cut out a piece. And so, to tell you the truth, I think this was art. I think he chose the amplitude.
I was just going to say, is this linear run?
This was art. This is linear.
Okay.
But I'll show you a nonlinear run in a moment.
This picture?
It's really from the code, but he chose the amplitude.
No, but this can't be linear. This is
So the island width-
early non-linear.
It's
Right?
no. You can run linearly and get this opening up.
You get the island linear.
Sure.
I thought you wouldn't see the island if it was linear because it's 1 and 0 amplitude. And as its amplitude becomes comparable to rho I, then you're in the nonlinear regime. Maybe I'm not.
If you turn off the nonlinear terms, then you can just keep right on going.
Well, Benito's point is well taken, and by the time you can see the island, it's probably linear theory.
But this is a purely linear run.
I'm just saying that he turned off the nonlinear terms, produced an island, and said, voila, there are perturbations that have this parity. And this was a nice little project because he wrote this code which produced the Poincare sections from a given A. And what we were seeing in Vienna in March was that people were just getting back around to that 8 or 9 years later. So David did a lot of good work in finding rational surfaces and looking at what the consequences were in a ballooning coordinate system. So
So what is that ballooning structure you just showed before? What that means went to real space? So I guess the A
this
parallel-
is that.
The A parallel I understand, because that would go to like a constant sine, effectively.
That's right.
Yeah, so we're not surprised that that's narrow.
Right.
What's the width of phi? If you go from that width,
This is so wide. This is so wide that this turns out to be radially really quite narrow.
right,
I'd say smaller, but we can pull it out and look for you.
Not ballooning at all.
Right, right. The problem, when you see these things that are highly extended like this, they're not ballooning at all. So our whole twist and shift is the wrong way to go. We're trying to resolve something that's not ballooning with a ballooning transformation, and so it's extremely slow and complicated.
But if that's like rho I in real in x space and that's constant sine in x space,
Yeah.
that's exactly what you expected.
Yeah, yeah, I think that's right. Well, we have to get the amplitude from nonlinear. Okay. So the first mention of the instability that we came across was Hazeltine, who did it in a cylinder. Focused again, the key parameter was the collisionality compared to the frequency, and needed the velocity dependence of the collision frequency to get it to work out. And then Jim, with different people, and Marilyn, did the whole thing in more detail. Later, Peter, who decided to skip this, I guess he had enough of this in 1981, did the thing in toroidal calculation along with Jack, and this was one of Steve's first papers, worrying about whether the various combinations from trapped and passing particles and how that all worked out for this mode. And as it turns out, there are big changes. I don't want to go through what they thought they were going to see because there were big changes in what was actually seen when people ran the codes. The winner turned out to be the Cato-Rosenbluth paper. This did the best job, and Jack and Steve paper flamed out, so it's too bad they're not here.
Neither of them is here.
I know, yeah. So this was my target for generating a conversation. I assumed they would be here to be insulted.
Oh, I think this is why they're not here.
What? Yeah, this is why they're not here. Yeah, they knew the answer, right? So we were using a collision operator with David, which had the pitch angle scattering and very strong gridding near adjustable mesh near all the boundary layers and trap passing space. So we were resolving these boundary layers, and in fact that was a cover of Physics of Plasmas about 4 months ago, a picture of the velocity space. Yeah, one of Michael's pictures was the cover of Physics of Plasmas, just showing the grid and how it's resolved around the boundary layers.
Was
But
the result of the cover?
But hold on,
Yeah.
This wasn't the same collision operator that they have now.
no, but it was the same grid.
Is it?
Well,
Same-ish.
same-ish grid. And what David did, since there were these predictions that the energy dependence was so important, was he simply took the 1/e to the 3 halves and set it to be constant and replaced V with V thermal in the resistivity or in the collisionality expression. And the growth rates really don't change that much. It's very,
So Bill, can I ask that?
yeah.
Is the dominant, say for an STX or something like that, is it the collisionality dependence between the trapped, untrapped particles? Is that the dominant drive mechanism for the thing?
No, I think what we thought was the trap particles seemed to matter, but the dominant things seemed to be, it looked a lot like the slab thinking. It's
So it's
just
still
grad
the
T
slab-
driven.
the slab-
It knows about the curvature, but the trapping didn't seem to be as important.
Okay. So it really hasn't changed that much?
Hasn't changed that much. And it's extraordinarily hard to get nonlinear simulations.
So hold on. So if I was to plot slab results on this graph, would they sort of overlap the line?
I'll look. You also set us some tasks so that we could come back for this in a week or two.
Because this looks remarkably like I remember from past
Yes.
history.
Yeah, yeah.
Nothing moves in
I mean, if Yuska actually has now.
We were in stasis.
They just stayed in
Yeah.
sometime.
Yeah, 1977, I think, was the date on that paper.
You might be forgetting more than we are.
So David did a bunch of shape variation and found, some dependence on the, this one is curious. I think this is probably this guy. Found some, variation as he moved the aspect ratio around quite a bit, but not much. And so shaping was not that big a deal. Let's just move along because I want to get to the parts where you care about. When you had a very large trap fraction, because he went to, the growth rate increased at low collisionality and decreased at high collisionality with a low trap fraction, so that's what he's varying. Then the energy-dependent collision operator made more of a difference. So we have a zoology. We have some sort of taxonomy, but not a lot of understanding. But there's lots of good simulations that we can compare with. So to summarize what David found 3 years ago, microtearing is driven by grad TE. It's a big mess. He and Jack, and I will distribute this to anyone who wants it, have a very nice, long, very careful series of comparisons where they turn off one term at a time. And then this energy dependence wasn't very clear by the time he left, and the mode is not actually that affected by aspect ratio, but what I think is going on is we don't care about it at normal aspect ratio because it's completely swamped by the usual microinstabilities, ITG and those other kinds of things. So here's the Howard's reactor in his backyard. This is the ST power plant. So they went for very high elongation, very low aspect ratio. And again, let's see, so this is B as you go around the field from minus pi to pi. And the cool thing about this machine is there's so much leaning, the plasma is leaning so hard on the outboard side that B poloidal increases here. So you get a lot of drift reversal, lots of great things happen. You stabilize lots of the usual instabilities, but you're still left with microtearing, and it's still a dominant player if you were to try to build one of these things. And here are some of those instabilities. So he completely stabilized in Howard's machine. Howard stabilized, whoever did it. Got rid of the electrostatic instabilities, primarily from these drift reversal effects from Shafronov shift stabilization. But when we put in electromagnetic, we got these tearing parity things. And now things get a little more complicated because we saw things both at long wavelength. This is K perp rho I of 0.4. Oh, it's here. Good. So KY rho of 0.4 and at short wavelength, K perp rho of 6.
This is the same mode?
No, these are instabilities. Both have tearing parity. I don't know if we call them microtearing or not, but they're instabilities all over the place.
Is it drawing the same?
Yeah, grad TE.
So that's curious because you'd think that if you have the long wavelength mode, it's probably because omega star is small, maybe compared to new EI. And yet you're still getting these large K rho modes. You'd think that omega star would be so large that it would be stable.
Except that this one is probably more electron, well, I don't know. The FLR on the ions is changing completely, and you're killing off if the omega star type stabilization from the ions is important here, it's completely wiped out by FLR when you go there. So maybe that's why it reemerged.
But I think it's not important long wavelengths either. I'm sure if you do adiabatic ions on the long wavelength,
You get this back.
you get basically the same
Yeah.
thing.
Fine. I don't know. I don't know.
We have tested it.
Yeah,
So
I hear you.
Even at lower KY. So I think from that point of view, there might be no major difference between the two.
And so the fields here, this is the phi perturbation, the A, and this is delta B parallel or delta J perp, or delta A, yeah, A perp. This is delta B parallel. I don't know why I wrote A perp there. It gives you J perp. Okay, let's move ahead. I wanted to show you that he did a series of nonlinear simulations. So I would like us to move in this direction while we're here. So he set up a box. He looked at the amplitude of the islands as time. So there's period of growth, and then it tried to saturate. And then depending on how he dealt with the highest Ks in the box, and this is very similar to problems that Paolo and Barrett have reported in Z-pinch simulations that were electrostatic. Depending on what he did for the highest Ks, we have a model. We have a fake hyperviscosity available to people that use the code. And if you set the coefficient to 0, finally the code would crash. And if you had any other value of the hyperviscosity, and it's normalized to the highest Ks in the box, so it's only affecting the very highest Ks, it seemed to continue and saturate, although there's an event here where things suddenly change. And on a log scale, it doesn't look like much, but I'll show you what happened here. So this phase, it didn't look like nothing seemed to depend on this hyperviscosity, but in the later time, huge differences appeared, and we could never get this resolved. And this drove Michael Barnes to go invent a new collision operator, and then he worked with Ian, and Ian got the collision operator, Michael put it in. This was all to try to get this problem fixed. That was the primary drive for why we were including more and more physics in the collision operators, because we were trying to stabilize the high Ks.
So Bill, was this KY or K perp?
It's mostly KX. It's the high KXs that are giving the trouble. So he had a modest number of toroidal mode numbers and a very high resolution in the radial direction. So here's a picture of it. So here's this is a Poincare section before the spike event. So these are J parallel contours. So you have a lot of resolution in the x direction. These are gyroradii, and this is a cutout. So we have lots of resolution in here, and you can see there's some island structure trying to form, but there's good surfaces. Nothing's going through here. So looks interesting. And then that little spike, say there's a spike here and then another one, and then it depends. Even here, when we had the hyperviscosity, there could be a spike and then it would go into some state. Huge change in the topology. So this is before one of those spikes, and this is what the Poincare sections look like after. We get stochasticity, we have, and it doesn't heal. The code sits in that state and then it's in trouble. So this is clearly not what was being seen in the Z-pinch calculations, which were electrostatic. There were problems, other problems with electromagnetic there at long wavelength, but it's entirely possible that there's issues that need to be thought through at high K, electrostatically and electromagnetically, and this could be a symptom. This might not be interesting to microtearing people at all. This could just be a problem. And the thought that I have is that one thing we've learned from what Gabe and Tomo and Alex have been doing is that the velocity space resolution should go up with the real space resolution, or you're not going to be able to get the phase space resolution that you need, and to resolve nonlinear phase mixing and the other things like that. So if any of us were holding velocity space resolution fixed and going to extraordinarily high spatial resolution, there's no guarantees on how that's going to work out. So this could be a sign of that.
So, hold on. So for this reason, we don't actually have a plot of saturation amplitude versus anything.
This seemed to be saturated for a long time.
Right. So
Okay? So I was pretty happy. And then David insisted on running longer and ran into running, same thing Paolo did to us. Insist on running the code so long. And then you would have this reasonable looking kind of patterns go boom. And then it would sit in this state and never recover.
So you're saying these are physical, right?
No, I don't. I wanted to, the discussion is, I think in a week or two we could make serious progress on, with the work you've done and the other work that's out here, to talk about what it is we think we need to do to discern whether this is physical or numerical. It clearly ends up a numerical problem, but is it a physical thing? And here,
This is an excellent one.
so David's arguing, no, this is good stuff. So here's all the different kx modes as a function of time. So here's the high k's. Here's some mid-range k's, and here's the low k's that participate in the instability, okay? So everything's fine until you get to these spiky things, when suddenly the high k's come up, and that gave rise to those Poincare plots that I showed you. What they were very worried about is this is a zonal flow amplitude, and it's slowly going up and finally possibly interacting with things in some bad fashion that we don't understand. So there was but overall you could say there's secular changes in other modes here too. Okay. Let's see. So these.
So Bill, I'll just say one thing. When we were looking at hearing mode evolution with GS2 with Powell's
Right.
saturation regime, I think it was later Tomo that looked at it and found that once the mode saturated the velocity space resolution, you had
It's
a
terrible.
very, very short time before you completely lost your velocity space.
Good.
after saturation.
So that's very
After
interesting.
Right after saturation, it could be run only a short term. They had put this diagnostic in there to monitor the velocity space resolution, whether it was adequate.
So what happens after saturation that's so special?
Could be the stochasticities mixing up space and bringing perturbations together that would, if you get that much spatial mixing, you're going to have a large amount of velocity space mixing as well. Yeah, so this was using the velocity space monitoring that Michael put in? Right.
So Bill, this is just 8 modes in KY.
Right. And
Does
500 or 1,000 in X.
Does that look like it's okay? Probably not.
Well, the instabilities were at 2 or 3, and it was all we could do. So I think at this point maybe we could do better.
Do
Do you know, maybe you could have thought of that, the KY spectrum of anything, amplitude?
I don't have it, but we could look.
But you know what it looks
I have the
like?
data. No, I don't know. That's the problem. I don't know what it looks like. So that's interesting. So velocity space resolution is the thing that we consistently did until around 2008. Everybody was using fairly low velocity space resolution. And only recently, since Steve started pushing us, have we gone to very high.
Did
Yeah.
you say that you have 8 modes in the y direction there?
Yeah.
Is it a coincidence that there's 4 islands on the boundaries of the box?
No, I think that
That's
we've
exactly-
gone to, we've done, this
that's
has
the
fallen
grid scale.
apart.
Yeah.
This has fallen apart.
No, but before that, in the previous picture, it's already at grid scale in KY, right? You have
No.
4 islands on the.
1, 2, 3.
Look at the boundaries.
1, 2, 3, 4.
Yeah, that's grid scale in KY.
No, 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 the spectral K of 8, so you could get up to 8.
Well, this is whether you count periods or half periods.
Well, I'm counting. I'm saying that we should be able to see up to 8. And this is the same simulation a little later. 1, 2, 3, 4. It was holding together for a little while, and then it didn't.
But it would be interesting to look at the KY spectrum, really, if you see a shift towards lower values in time. That's what it looks like from your spatial plots. That's something, maybe something to the second or third KY mode,
Yeah.
then it shifted to the first one,
Yeah.
and then the system
Couldn't deal with it and blows up.
yeah.
And that would be like some of the failure modes that you guys have, where the longest mode is actually the one that blows up. So I don't know.
We've seen all the
You've seen everything break, yeah. So that's, the idea is to drive a conversation. So we have a kind of instability. Now, the two ways that people are looking at this instability, I think, correct me if I'm wrong, Ryuska's set up a situation just like regular tearing where you set a perturbed temperature gradient in the simulation and fixed. Okay. Okay. So this instability, the way David's running it, you don't have to have an island, you don't have to have a B like this in the box. You can just run off of a regular equilibrium. So what do you guys want to do with this topic, not this specific set of issues?
Well, if it's clear that the temperature gradient is what drives instability, maybe we should start with slab simulations of this. rather
That's what you did, right?
Which is what Huski's doing.
Yeah,
Where presumably you can get more resolution.
I did without tearing and without ETG and just temperature gradient. So
Right.
I guess that's my opinion.
Yeah. And you got good agreement with GLAD and so forth, right?
With temperature gradient.
Electron temperature gradient.
So what exactly is microtearing?
Odd
Just
parity,
temperature
odd
gradient?
parity instabilities.
Just that's it? But what's the minimum set?
Delta prime is such that you wouldn't expect tearing, and those are normally at long wavelength. But if you get to short enough wavelength and you have a strong temperature gradient, you can have a whole sea of instabilities with this tearing parity.
So let me ask a very stupid question. If I take an MHD code and I put it and I set it up such that the delta prime for the background magnetic field is negative, so it is not tearing unstable, but I also insert a background temperature gradient, will it go unstable?
No.
No.
It won't.
So
You
you need
need
a
the-
filler.
It needs a
No,
filler.
no, you need the energy dependence of the collision operator. You need the energy dependence of the collision
But
operator.
he just showed correctly that you don't.
Not always. In a torus, you don't.
Okay,
Well,
but
it's just in
I'm talking about the slab,
Yeah, the slab. I think we should focus in on a slab. That was the motion a moment ago.
You need the energy dependence of the
Yeah, that's,
collision operator.
that's what Hazeltine showed this, in this 1975 paper or something.
Right, 77, I thought.
And then when I did this first linear theory, the tearing mode, I included that energy dependence, and then you get all these temperature gradient
But,
instability for both.
why is that? Is it because do you somehow get T by dB of U somewhere?
No, it doesn't come in that way. I mean, we never really understood the physics for why this happens, but,
But you said you
but you know,
derived
this
it.
is not anything unusual, because a lot of these trapped particle instabilities,
Is this a tripod?
No, I know it's not, but they put in the energy dependence of the collision operator in those models, and they were getting instabilities, and I think it was for the same reason, even though it wasn't
Wait, this
microtearing.
statement that you need energy dependence in the collision operator, is it an analytical statement or numerical statement?
Analytical statement.
Analytical,
So
definitely.
this was done analytically.
So how does it enter then?
Okay, it's been a few years.
Here are the papers. Nunu asked me to gather the papers, and here they are.
I can go
We
back.
don't need the papers, we have.
I can no, you can't ask a guy to remember what he did 33 years ago.
Here, I can tell you that you wind up with this integral, of a energy integral of 1 over omega plus I nu downstairs somewhere. And you do that integral, so you try to do an expansion, for example, nu less than omega, say you're in the.
You get the resonance out of the energy.
No, you don't get a resonance, but you get these, between the I and the omega, you get, an imaginary part of epsilon, which depends on the fact that you have energy dependence in that collision operator. Because otherwise, the omega plus I nu could be pulled out of the energy integral.
So you need to have something to do with gradient.
Yeah, so I mean, that's not physics. This is not physics.
No, that's
It's a
good.
mathematical statement,
But that means effectively it's a resonance.
It's not really.
No, it's not really a resonance.
Well, if I
It's more like the thermal force. You get no
so-
thermal force if you don't have a velocity dependent
So-
in Brzezinski.
Yeah,
And
so
this is if you
this paper which claimed this is a time-dependent thermal force.
right. That's the way he
got
looks
it
at
out
it.
of a Brzezinski analysis, which was basically like a time-dependent.
And that's the .71 grad business.
So
Yeah.
why
Yeah.
do you need the temperature gradient?
Because the
Because
temperature
it all
in front
multiplies
of
the
it,
temperature gradient.
the temperature gradient has also an energy dependence in front of it when you do that.
V square minus blah blah.
Yeah, right.
V square minus 3 halves.
And the omega star n does not.
So the minimum set of ingredients is a temperature gradient and an energy dependent collision.
In a slab.
Yeah, in a slab, and that's
Flat density profile, is that right?
Flat
Density
density.
stabilizes it very quickly.
right, but you can get away with flat density.
No, you need flat density.
Well, you need, some ratio, right?
Yeah, I mean, it's just much more convenient not to take density at all.
So Nunu's microtearing challenge, right, is grad T Ian's energy collision operator.
Well, any collision operator.
Whatever.
It's just the nu out front. It's not the energy diffusion.
Fine.
It's the.
All right, can we have,
it-
we can have crook even better. Do we need velocity space structure? We don't need velocity space structure, right?
Let me think.
Let's do crook.
But you need.
It means a fairly sophisticated crook.
That's fine. Yeah, no problem.
Is it true that because delta prime is negative, that at least as far as the magnetic energy budget is concerned, that the island, making the island is actually costing the mode energy?
Yeah, the bending forces are stabilized.
Because of that, is there a critical temperature gradient?
Yes.
Yeah.
Below which
Or
the-
maybe that saturates it. Like it's
Uh-huh.
non-linear.
So what do we know about saturation amplitudes, just proportional to delta?
I don't think we know a lot.
That's Jim's.
That's why I was asking earlier, right? So your plots run for very long.
How fast is it meant to grow? That is good. There's collision frequency somewhere in there, right?
It does
You
depend too
showed
much
us
on-
the sweep, and so it,
Yeah.
It's got the same growth rate as ITG.
Yeah. No, there's a collision frequency.
Um,
No.
okay.
ITG
These
is-
numbers up here are comparable. I'm saying it's not.
No, I mean, what does it depend on?
Ah.
I mean, does it get less when you decrease collision frequency?
Wait,
So we had two different regimes
You
depending
get
on the
minus
trap
less,
fraction.
but,
You get different regimes depending on trap fraction.
yeah, that comes with it.
Nu EI.
Saturation amplitude, did you saturate?
No,
No?
just reading.
What? Sorry?
Just reading it.
No, so we don't know saturation.
What's your normalization here, Bill?
Gamma is normalized to R over V thermal I.
And nu also.
And nu as well, right. Normalized the same.
Physically speaking, does anybody know why delta A parallels is even necessary for this?
Delta delta A parallel.
Yeah.
I think you get driftways, which are driven by the similar mechanism, but it's just that they're overwhelmed by other instabilities. And so, it doesn't make any difference.
But I mean, this mode it's costing this mode something to make an island, and yet one needs to have electromagnetic that's enabled to see this.
Yeah, you need the electromagnetic, and it always has that parity. We didn't see the other parity.
You never saw the other pairs.
Physically, is that
Yeah, but you don't need.
is that just
It's
is
not
it
healthy.
changing the electron response to an adiabatic or something that it's necessary to have delta A parallel? I mean, delta A parallels
Yeah, it could have many roles. Yeah,
require purely ideal.
I don't know.
Barrett, sorry, I don't understand your question.
He's pointing out that
How else would it reconnect?
it doesn't need to reconnect. He's saying there's an instability driven by grad TE, and it's costing it energy to put a magnetic perturbation in, so why is it bothering?
Does it actually reconnect?
Who cares about reconnection? Hang on, let's
It does
focus on
reconnect.
this question.
It does
But-
reconnect.
No, we care because maybe you can run it electrostatically.
No, that was early in this. It's,
So
I mean,
Yeah.
for some reason, Barrett, it seems to be the case, if you crank up, so there's a critical R over LTE. And if you increase that number, then there will be some threshold, of course. And it turns out that in some cases, for certain parameter ranges, this critical gradient is somewhat lower than that for trapped electron mounts, for example. But they're in the same ballpark, but there might be, 20-30% difference or something.
I have some vague memory that
That's all.
if you looked at the hierarchy of modes, that you'll have, to lowest order, you have the even A parallel mode, and then if you have a nice enough gradient, then you'll get the odd A parallel mode, and then several. But,
not in general, but for this.
for this,
So
so.
I've not seen the odd A.
So you've never seen it?
Well,
on the
David did the work. I haven't seen it.
Yeah, okay.
He never presented that to
Yeah.
me.
Maybe
So maybe that lives there. We can force parity and look. This is something we could do in a couple of days. There's a parity switch in the solver.
So in these conditions, the temperature gradient for which, the minimum temperature gradient for which the microtearing goes unstable, is it also ETG unstable?
It is ETG and ITG stable. That's what this says.
Stable.
We took, in some configuration, it is possible to set up a configuration where you have enough stabilization from Shafronov shift type effects that you completely stabilize everything else. But we've not found a way to get rid of this. So this thing pops up whenever you do some kind of exotic configuration where you've stabilized everything else linearly.
How about in a slab?
Don't know about a slab. I don't know if there's a regime where we can find this without the other usual characters, right? That would be worth knowing. On the other hand, Barrett's done, I think, some work, and others. There's several instabilities which we call various names, and they all frequently will have a tearing parity. And they're not really reconnection or tearing type instabilities, they just have this parity, and
Like
so
which one?
ITG. There's odd parity ITG all the time. There, sure, absolutely. Resisted ballooning has odd parity. We were looking at it.
Odd for
Yeah.
your ITG?
No. You can find them. They exist.
Really?
Yeah. You haven't seen that.
I wouldn't call it an ITG mode then.
Well, probably because you can choose the pair.
Yeah, so we turn off. Well, he's got an eigenmode solver. So,
All right, yeah.
but
In
we,
your nonlinear simulations, you don't specify parity, right?
Correct.
It
That's
just
right.
goes.
That's correct.
Bill, can I ask?
Yeah.
The non-linear simulation that David did, it's very, very extended along the field line. So,
Actually, that just means very high KX resolution in the box. With the twist and shift,
But if it's not ballooning, then doesn't the non-linear way the box is set up assume that it's going to be larger and the output may thing then?
yeah, that's why you need all those stupid KXs to resolve it. That's what we're saying, that we're using the wrong coordinate system for this instability. So we have to go to extraordinary resolution in one direction to get what would be simple if we didn't do twist and shift. Exactly right. But he did resolve it.
Well, but it's just a fact that this mode has a very anisotropic structure in itself. I mean, that's just its nature, right? Independent of our choice of coordinates. I mean, it just turns out that delta x needs to be way lower than delta y typically.
Well, I think I like Howard's way of saying that this just isn't ballooning, and so it's putting islands all the way around, not just at the outboard midplane.
Yeah, but even
And
if
so our
you're running-
coordinates, by the time we get to back over here, we're trying to resolve a perfectly simple perturbation with a horribly sheared box. So we need very high kx resolution, but that's just because we've chosen a dumb representation. So an interesting question would be, can we run any of these codes? Does anybody have the switch to turn off twist and shift? And it'd probably be much easier to study this kind of instability.
In the slide, we don't have the same problem.
Zero magnetic shear, yeah,
You could do that, but
that's a good point.
It just has KX to
No. With magnetic shear, you have the same issues. We do twist and shift in the shear in the slab. No difference. That doesn't help you. But zero magnetic shear. So that's a task. Those of you that want to look at one of these papers, what we need is confidence that there's a slab system at zero magnetic shear where the only instability that we would expect to see is this odd parity tearing mode, microtearing. That would be great, because then we could study its saturation amplitude and understand whether the velocity space was going to pot, all those kinds of things without worrying that we're confusing this with some other feature.
what happens if you run non-linearly without the high resolution? Okay, maybe it's not a good description, but does it blow up or not? In some sense, you run a strange box
Yeah.
with very strange cells. I mean, very narrow.
Oh, I know the answer to that. So Clarice Bourdelle also quit doing GS2 calculations because of this instability. This instability has defeated several, bright people. Because what she too started looking at instabilities at high beta, where beta prime stabilization was killing off the good, the bad instabilities that we all deal with, and she's not running. So David found that he had to do these domains, 480, which is a huge number of field periods, right? If you, in GS2, with the boundary condition that GS2 uses along the field line, which is a particular boundary condition, if you were to cut this off anywhere short of 160 in this picture, so any normal box, in other words, if you didn't have those high kx's, you get a spurious numerical instability which has a much larger growth rate. So our boundary condition is incompatible with faking it for an instability with this kind of
I mean, your G
structure.
is an equivalent way of suppressing.
Yeah, but it's nice and smooth, right? It's not going to just.
The D you talked about before.
Yeah. That kills off
That kills it up in a physically.
in a smooth mathematically smooth fashion.
Mathematically smooth fashion.
And in particular, the boundary condition has to do with a Maxwellian entering the box from this side, moving to the right, and a Maxwellian entering this side of the box from there, and it needs to be at a particular. The field has to be at low amplitude, or it gets in a nonlinear. It gets in trouble. And the D gives you smoothness so that doesn't happen. Yeah, so we can't fake the box in our code. Now, maybe you can. And Gene may have a much better go at this, because you do the boundary condition differently as well.
Oh, we have two ways of doing boundary condition. One is similar to yours, I guess, and the other one is simply setting it to zero. But I think that, first of all, you might save a little bit of effort along with V9. I'm sure if you reduce the X resolution by some moderate factor, you can still get away with that. Because what we find non-linearly, so if you do a nonlinear simulation of microtearing, and then you project out an individual mode at an instant in time, you find that the turbulence will damp away some of your tails. So sometimes the turbulence helps you confine the mode a little better.
It doesn't make big. So in Gene, does it blow up? Do you have the same problem? Or do you have a nice stationary space and
We fight with similar things, but we have a bunch of simulations that are steady state and
So you don't have
single
this
phase.
problem.
What's the
Parameters. Yeah.
Oh, the difference is, correct me if I'm wrong, Frank, when yours blows up, it's the lowest KY in the box running away.
Typically, yes.
And these kinds of problems of excitation of the highest Ks, and you can see that these high Ks are suddenly getting excited, and these are the problem.
Again, high Kx, you say, not Ky.
Well, there's no,
There is no high Ky.
right.
Well, it's a relatively high Ky.
Whoa.
No, I'm serious. What we see is, so we run in a parameter regime where linearly everything is confined at very low Ky. But non-linearly, everything spreads out into a region where linearly there's nothing.
Uh-huh.
We're quite surprised, but it's a nonlinear effect that pushes things. We kind of understand it now. And I could imagine if you cut this off very soon in Ky space, that might also cause trouble. I'm not sure, I mean, these different parameters, but.
Just a regular tearing.
I'm just saying that at least for our parameter set, if you, well, what we usually do is we're guided by the linear growth rate physics, right? So we do a growth rate scan in Ky, and everything's,
Yeah.
I don't know, up
You
to
find the
5,
bump.
and then you say, so if I resolve to 0.6, I'm there.
Yeah.
And I'm saying that.
But you need higher.
Is at least not true in our cases.
Okay. Well, so it's not surprising that the advice for the particular thing I put on the board is to use higher velocity space, higher K space.
Everything else.
But we want to bring more players into this too, so.
So Bill, what's the boundary condition in Astro GK?
Zero magnetic shear, so it's periodic.
So there's no magnetic shear?
Yeah, that's one of the principal simplifications of the code. I think if there's a zero shear version of this, that would be really convenient.
Yeah, but wait a minute, why can't you just add shear?
You mean with a perturbation?
No, well,
Everything becomes field line dependent. All the K-perps and everything become field line dependent. So that's what I took out to make AstroGeek simple.
yeah, but treat it as a, you can still do it periodic, just have a periodic magnetic shear or something like that. Or I guess that creates a slab system with shear. Right, I don't see why.
You want me to put a large amplitude B in that would
Yeah,
give
yeah.
shear. Yeah, yeah, that's what I thought you were doing. That's what we were doing in Vienna. So we were putting in a B.
So, but I guess the trouble is there is it, maybe you're dominated by grad TE instability or something as opposed to this thing. So is there some regime of sheared slab system where this thing can actually beat out other stuff?
Well, I think if we go to strong Shafronov shift toroidal, we can kill the ETG, the drift type instabilities, and be left with this.
You can change the temperature ratio.
Maybe temperature, yeah, that's right. Make TE over TI large.
Yeah.
If we go to high TE over TI, we'll kill off the ETG. Yeah, that's a good idea.
Okay, so then you can get, if you have a slab system then
Right.
where you have some fake shear, then you can just do Astro GK.
Do we need magnetic shear for this? I don't think so.
Well,
Well, where's the surface?
The instability will exist, but I think you're not going to answer a lot of your questions.
Right.
But maybe we can answer one thing. For example, what's saturation amplitude in terms of rho I?
Yeah, but I think the magnetic shear. So a magnetic island, as you draw it, is not going to exist in a non-shear system because your amplitude of the magnetic island comes from balancing the twist in the magnetic field with the perturbation. So in the absence of that, you're going to get
K parallel can be zero everywhere with convective cells. And it's a
Right,
mess.
it'll be convective cells, magnetic convective cells.
Right.
It'll be quite different than what you're actually doing.
So I'll send out a note to anyone. Can we post this somewhere? Or do you have a note of people that are interested in this? You have a list.
Post what? Apple case these.
Well, yeah, some notes of this discussion and a proposed next step.
We can subtract it.
Okay, so let's do that. It's 4. Let's take a break.
Okay.
Good.
There's